Uh, as you, as I think you would know, we're over here at these Friday night sessions. We are doing tournament training. It's open, of course, to not just people who will be participating with us in HMMT and uh, other tournaments down the road. It's open to all, but what we'll be doing will be quite relevant to HMMT. Now, last week, we uh, did a full HMMT general test to get quite a feel of difficulty and uh, perhaps also the time conditions of uh, HMMT tests. Today we'll be doing something a bit different. I've compiled myself I think an instructional compilation of problems. I'll be giving that to you shortly. And uh, I think these problems they're not necessarily designed to be uh, very precise in terms of uh, closeness and difficulty to HMMT. I think it's reasonable in terms of difficulty. I think it's uh, close to an HMMT, but you got your real HMMT test last week. This week we'll be doing this test for the instructional purposes. The problems I think are instructional, and they each highlight some important techniques I think people may or may not know. So, all right, let's I'll upload the test into the chat here. So let me pull this up. Cool. Send it to everyone. Oh, no, we didn't send it to everyone. Let's try that again. Okay, do you guys see the file I sent in the chat? Well, can I get a confirmation? Do you see the file in the chat? Yes, okay, and we'll have you guys download this. Let me also, so we'll be doing something like 50 minutes of this. Once again, this may be harder, maybe easier than actual HMMT. Don't use this to judge HMMT difficulty, but we'll do something around HMMT time controls for purposes of having enough time to explain everything. So I'll put this here to annotate. Oh, is my screen sharing paused? It should happen. Nope, can't do this. Okay. Okay. I'll just make a note here. So for anyone who comes, perhaps late, you might not see the test in chat. Let me know. I'll send it to you once again. But HMMT training test. Apparently I can't. Okay, I'll try stop screen sharing. We'll move this to my other monitor and try this again. I'll just hit. See the chat. Okay. With that in mind, let's get yourself started. We'll see you on the other end of the 50 minutes, and we'll explain. Yeah. All right, that's time. Okay. Cool. Okay, so that's 50 minutes. Really, this isn't the point of this isn't to time yourselves, and it isn't so much a time test as it was last week, but we nonetheless still have to get going with discussing all the problems. So let me pull up some, okay. Okay, let me pull this up. I'll re-share so that you guys see this. Share this window. Okay, let's start discussing this test. So, by the way, how did this feel? Just more curious in terms of difficulty, in terms of your familiarity with these types of problems. How is the test? Any thoughts? Seemed harder than normal HMT, right? Okay. You might have missed this one when I said it earlier at the beginning of the session, but I tried to make this a reasonable difficulty, but difficulty wasn't the highest priority here. We had a real test that simulated HMMT difficulty last week. This week is more of a test that I think you guys would find rather instructional. Anyway, okay, let's get to the problems. And I'll try to explain them with insight and with explaining motivation, explaining how you would approach the problem, so that this is what you get is much more than just what you would get from reading the solution. Let's start with number one. So the teacher writes the alphabet on the board and erases letters one by one in random order. So we want the probability that at some point the letters I and U will be next to each other. So well, you've got, we'll count the letters later. Okay. Okay. So the operation of erasing letters one by one from the board, well, you can express this in terms of just what the letters are erased, right? What are the erased letters? The erased letters are just a permutation of the alphabet. So it's going to be A to Z, permuted in some way, and this permutation defines the order in which we erase letters from the board. Now, what about the condition that I and U are at some point next to each other on the board? How do we rephrase this condition with our representation of this operation, this whole process with a permutation of the alphabet? After all, a permutation is a lot easier to study than just a series of 26 operations. Well, if I and you are at some point next to each other, then that means that I and you were not erased. Yes, exactly. That is exactly right, Julia, because I and U have to be not erased at some point, and yet all the letters between I and U have to be erased before I and U. So all the letters from uh, J to T have to be erased before I and U. So that means J. This implies that J, the letters J, K, L, so on and so forth, up to T, are all erased before I and U. And it doesn't matter which of the letters, other letters are erased in what order they're erased. Just the letters between I and U. And there are, well, J, K, L, M, N, O, P, Q, R, S, T. So there are 13 letters between I and U inclusive. So out of these 13 letters, we need J to T to come first. Okay, so out of 13 letters from I to U inclusive, again, we're only looking at I to U in the permutation. You can have other letters in the mix, doesn't matter here. Out of these 13 letters, J to T come first. And of course, each of our permutations are equally likely. The number of permutations for which J to T come first is, well, 11 factorial times 2. So in our, the number of permutations of, so times 2 is important here because we can have so we have all permutations of J to T for the first 11 of the 13 spots, and the last 2 of the 13 spots can be I or U in any order. 11 factorial times 2 divided by 13 factorial total, and that gives us the probability of 1/78. Okay, so when it comes to combinatorics in general, rephrasing the problem is always a powerful tool. Think about how you can think about the various ways of rephrasing and think about which one would be the easiest to work with, and try to determine what the conditions are equivalent to in a problem. All right, number two. Okay, fair coin is tossed repeatedly until 2021 consecutive flips are the same. Compute the probability that the first and last flips of the coin come up differently. Let's see. Some of you may, now one way I could explain this is some of you may be familiar or have heard of a problem that goes, say, a fair coin is flipped repeatedly until 2021 consecutive flips are the same. And the question would be perhaps, what's the expected value of the number of flips that you make? And I won't go too much into detail into that tangent, into that question. It's solved similarly to this question, so just work it out for this question. But drawing on inspiration, if you happen to know what that may be like, the way we do this is states. Okay, so let's say we've flipped so far. We've got a sequence of H's and T's without loss of generality. We'll see. Say it begins with H and H T T H T H H. Here's our random sequence of flips. What we're interested in with seeing this random sequence of flips is, well, probability. We want to compute the probability that we end that our last streak is a streak of 2021 T's. And well, over here, we don't have any streak of 2021 in the sequence so far. So really none of the flips that have come so far really matter, except HH, because only these flips here have the potential of forming 2021 consecutive flips. Okay, so right now, well, let's look at this in terms of streaks of T. That's what we're looking for. So right now, the ending here, we're looking at the last streak in the sequence. This is a streak of zero T's. Right. Or rather, we could say it's just that I think we only need to concern ourselves with whether it's H or T, so we'll say it's streak of H's. Okay, well, here's how states work. So let P be the desired probability that equals probability. Okay, well, let's start from the beginning with state. First flip, well, let's say our first flip is H. Then if as we keep flipping, if at some point before 2021 flips, our first streak of H ends, then so let's say we've got HH, so on and so forth, HT, where the streak may be anywhere between 1 to 2021. If we've got such a sequence of flips, then well, after we have our T, then it resets. That whole starting streak of H's don't matter anymore. So then we're just left with something starting with T, and we want to find the probability that now our latest streak is T, this T of streak 1. What's the probability that will end with a streak of 2021 T's? And in this case, the probability that we end with 2021 T's is now our starting number now is T. Starting flip is T. So it's just the same problem, but the complement, 1 minus P. P being the probability that the last flips are different from the first flip, and now it's the probability the last flips are the same as the first flips. So well, the probability we don't have outright a streak of 2021 H's is 1 minus 1 over 2 to the 2021. Is that right, or is it 2020? I think it's 2020. Yeah. Okay, so that times 1 minus P. So first of all, P equals this. This is the case when we don't outright have a streak of 2021. And if we do have a streak, then it doesn't hold. That the last flip is different from the first flip. Okay, so you would just solve this. You would get 1 minus P. Let's see. This, so P is equal to 1 minus 1 over 2 to the 2020 divided by 1 plus, so 2 minus 1 over 2 to the 2020, which will simplify as 2 to the 2021 minus 1 denominator, and 2 to the 2020 minus 1. the numerator. Okay, so that's your probability. As expected, the probability is slightly larger than 1/2, but it's not equal to 1/2. And that's number 2. Always have the impression of. We've got to, we should speed up a little here. Number 3. So we've got a function f of n, where f of n is the largest odd factor of n. And we want to find the sum f of 1 over 1 plus f of 2 over 2 plus so on and so forth. Whoops, forgive me. Okay. All right, so start out by, what do we do? Let's start out by analyzing, well, f of n is not particularly interesting, but f of n over n could give us some room for making discoveries or making observations. So what is f of n over n equal to? F of n is the largest odd divisor of n. So n divided by f of n would be n divided by the largest odd divisor. So it would be a power of 2. So this is equal to 1 divided by a power of 2. The power of 2 specifically being the largest power of 2 that divides n. Okay, so naturally, this means we want to sum this up by looking at the largest power of 2 that divides n. So, for example, if n is odd, that would mean that we have, well, we have 20 and 48 over 2 values, such values of n. And for each value of n, f of n over n equals 1. So that times 1. If 2 divides in and 4 does not divide in, so 2 divides in, 4 does not divide in, then we have, well, we've got 2048 over 4 such values of n, and the value of f of n over n is equal to 1/2. So on and so forth. It becomes quite clear to see that the well, this is equal to 1024. This is equal to 1/4 of the previous number, which is 256. The next number would be 1/4 of this, 64, so on and so forth. You can see that this is added all the way. Well, it's added away. It's not added all the way down to. It's not added infinitely. The smallest term would be n equals 2048, which would give us 1 over 2048. But in any case, we have this geometric series, 1024 plus 256 plus so on and so forth. And the terms less than 1 add to roughly 1/3. So it's going to round down. And thus our sum is, you can add this all the way to 1. You'll get that this geometric series has a sum of 1365. All right. Oops, forgive me. Oh. See if I can get back. Okay. Okay. Sorry, some keyboard shortcuts are not doing things are doing annoying things here on OneNote. Anyway, number 4. Let's look at number 4. So we're given an equilateral triangle, we've got a point that lies on the incircle. Usually helps, by the way, perhaps to draw a bigger diagram, but as long as you know what's going on, and if your diagram's too small, it isn't functioning, just draw another one. But as long as you know what's going on, I think you're fine. In any case, so got a point on the incircle. Its distances, its closest two distances to the sides are 1 and 4. So that's 1. And we've also got this perpendicular here, and that is 4. Forgive me for the small diagram. And well, find the length, side length of the equilateral triangle. Okay. The difficult condition here, one of the more difficult conditions to work with, is that the point lies on the incircle. How can we deal with the fact that the point lies on the incircle? Okay, well, okay, let's start labeling. Let's say that we've got ABC, and let's say this tangent is D. Well, let me, I'll keep this notation the same as I had before. Oh, okay, yeah. Yeah, all right. D, and let's call this E. Okay, well, first of all, let's see. Okay, first of all, one thing you would want to know is that for any equilateral triangle and a point inside an equilateral triangle, then, well, we're interested in the distances from the point to the 3 sides. What relationship can we get about these 3 distances? What we can get is that if you connect the point with the 3 vertices, forming 3 triangles, then you can see by area, each area is the base, half of the base times the distance, which is the height. Sum them up together, the area must equal the area of the whole triangle, which is half the base times the height. So the sum of these, regardless of the point that we choose inside, the sum of the 3 distances is equal to the height of the triangle, equals root 3 over 2 s. All right, that's good to know. Now, what about the integral condition? Well, one way to express the integral condition is, well, and here I'll draw a slightly bigger diagram, or maybe I could just zoom this in. Okay, well, you can see we've got a right angle here, right angle here. This is a 60-degree angle. This is a 120-degree angle. And furthermore, our point P being over here, what we have is P lying on the incircle tells us that this angle here is 120 degrees. Angle DPE equals 120 degrees. Okay, we could really hope to draw a bigger diagram. Let's see what we can do. I'll draw with ink the shape. good enough. Okay. All right. Let's hit A, B, C, B over here, E over here. Got a point P over here. What we know is that angle DPE is 120. Uh, uh, it's 120 and not 60 degrees here because we choose P so that it's closest to AB and AC. And we've also got the point where the feet of its perpendiculars, let's label them as M and N. All right, so angle MPN is 120 degrees. Angle DPE is also 120 degrees. So we want to think about, well, do we have a similarity here? Okay. Okay, well, what we okay, so we know this is 1 and this is 4. First of all, the fact that PM equals 4, that tells us. So if you look at P, okay, well, so I'll just draw part of the diagram here. We've got P, we've got M. One thing this tells us, for example, is that this being 4, we know, well, we know here we've got if we draw, for example, the line through P parallel to BC, then we've got a 30, 60, 90 over here. So this length is equal to 8 root 3 over 3. Similarly, this would tell us that our length here is 2 root 3 over 3. So that's very useful to know. So we can instead express the conditions of the length of the perpendiculars as, well, draw a line through P parallel to BC. The distances are 8 root 3 over 3 and 2 root 3 over 3. Okay. Another observation is, okay, let's draw this in and let's label the points here as, should we label them X and Y? Okay, so if you look at triangle DXP, okay, triangle D, let's turn this off. DXP, excuse me, this is similar to triangle, well, let's look at some angles here. So, all right, so in triangle DXP, first of all, we have this 120 degree angle X. Furthermore, we also have the angle at P. The angle at P is dpx, which is equal to, well, it's equal to half the arc, and that is equal to angle all right, so dpx equals angle d ep, and why is this? So first of all, we do have, well, let's start fresh. first of all, we do have that angle DXY equals angle XYE, right? These are all equal to 120 degrees. Okay, so angle X and angle Y, we've got the same. We've also got that angle, what else do we have? Let's look at XPD. Angle XPD is equal to angle PDE because we've got a parallel condition here. XY is parallel to BC, which is parallel to DE. So this is equal to angle PDE. Which tells us that, as a matter of fact, triangle DXP is similar to, let's get the order correct, EPD. There we go. And this is similarly similar to triangle P and PYE. Same line of reasoning. Okay, so what side lengths do we know here? Well, we know dx, we know dy. We want to find DE. That would tell us the side length of the triangle. And what else do we have? We've got, so let's let, all right, so, and the other lengths we don't know are dx and EY. But we do know dx equals EY here. Once again, XY is parallel to EY, so let's let that length be X, not to be confused with the point X. This similarity here that we just found tells us that, well, let's look at X divided by a corresponding side length, which is, let's say, PY. So we're looking at dx to PY, X over 2 root 3 over 3 is equal to px, which is over here, to EY, 8 root 3 over 3 to x. And this should tell us that x is equal to 4 root 3 over 3, which from which we can also get that, well, there's several ways to finish this now. One way is we can use our property here that we saw, that the if we can get the length of the height from P to DE, then that would tell us the altitude, length of the altitude of triangle ADE. So I'll illustrate this here. So knowing that x equals 4 root 3 over 3, we have distance from P to DE equals, what would this be? This is root 3 over 2 times this. So it's equal to 2, I think. Right, from which we can tell that the altitude of a triangle ADE, which is just half the triangle of our triangle ABC, and this altitude is equal to 7. So that would tell us that the side length is 28 root 3 over 3. Just a quick note here, I know we're kind of out of time, is that one way to spot this similarity here is to really just is a special case of, or a case of spiral similarity. So what's the spiral similarity? X and Y were more just points we defined to spot the spiral similarity, but the similarity that we have is, let's get this right. So let me make sure I'm I have different variable names here. So we've got triangle. Side note here. Spiral similarity. A spiral similarity just means that two triangles are spirally similar if, well, you can dilate if you can pick a point in the plane and dilate one of the triangles and then rotate the triangle, dilate one of the triangles about the point, then rotate the triangle about the same point to get the other triangle. And in this case, the triangles that are spirally similar are triangle so first we've got N P let's call this point and K, the projection of P to DE. If we call that K, then triangle NPK is spirally similar to triangle we've got, well, one of them is DPE, which in turn is spirally similar to triangle KPM. There we go. So I know we're quite out of time. Let me see what I can do. If you'll humor me, because if you've got to go, I understand this. But if you'll humor me, I'll try to at least talk through the remaining problems, perhaps briefly, more without working them out fully, so that you guys get the idea. It's really the idea that I think is the learning value here. So I'll quickly get through this. Number 5. So number 5, as we've got the condition root x plus root y equals 5. We want to minimize the value of root x plus 9 plus root y plus 16. And the thing about this is our condition is not easy to work with. Root x, root y, for example, you wouldn't want to square this because you would get a far nastier condition if you try to square and get rid of the radical in the condition. So squaring is not quite an option. As for inequalities, well, your problem here is the condition. So how do we deal with the condition? The way we do it is we let this equal a, root x equals a, and root y equals b. Then our condition becomes a plus b equals 5, and we want to minimize the value of, well, a squared plus 9, the square root of a squared plus 9, plus the square root of b squared plus 16, from which you can recognize that, well, this is Pythagorean, which just means that, well, the sum here is the distance from AB to the point -3, -4. So it's just the minimum value of the distance as AB ranges over this line segment from 0,5 to 5,0, and you'll easily get your answer for 221. So that's number 5. Well, number 6 is also, as like the other problems here, also quite instructional. So in a knockout tournament of 128 players, what's the probability that 2 of the players will face off with each other? Well, this is it's quite tricky. I think quite not an obvious thing to see if you haven't seen this before. It's really useful to know this. And this is how we do this. So the knockout is randomly chosen. The brackets are randomly chosen. So what we can do is, well, we've got 127 matches at various stages of the tournament, but still 127 matches. Matches between any two player at any point or are equally likely to occur. We've got 100. There are 127 matches, by the way, because each match eliminates a player. So, if we just look at Alfred, the expected number matches that Alfred would play in is, well, each of the 127 matches. The probability that we've got our Alfred in a match is, well, 1/64. So 2/128. Two players in a match out of 128 players in total. So this is the expected number of matches that Alfred plays in. And if we now look at Nigel, the probability, so so the number of matches that Alfred plays is also the number of opponents that Alfred will face. So the probability that out of these opponents, one of them is going to be Nigel, is just this divided by 127. So probability equals 127 times 2 over 128 divided by 127. Nigel out of 127 other players, and this is equal to 1/64. Okay. Next we have next is also a good problem. Number 7. We've got a cyclic hexagon. I've got a ready-made diagram here, so to save time, I'll try to copy this diagram here. Let's see if this works. Yes, it does. So we've got a cyclic hexagon where the sides are, we can label the sides. A bit of a spoiler in the diagram here, but we'll see why that is the case. Anyway, this is 3, 3. BC equals 4. DC equals 5. DE equals 5, and EF equals 6. Cool. So first thing, when we have equal chords, that means equal arcs, and equal arcs mean equal angles. So what are our equal angles? The fact that AB equals AF tells us that this angle here, corresponding to arc AF, equals this angle here, corresponding to arc AB. Same thing here. This angle also this angle equals this angle, which equals this angle, which equals this angle, and the two angles we found before, they're equal, and they're also equal to those two angles. So already a big observation we can make, which is that, well, your lines AE, DF, BD, and CA are angle bisectors as drawn in the diagram, which means that X is the incenter of triangle BPC. Y is the incenter of triangle EFP, EPF. And we also have that triangle. So that's the first point. The second point, and the third point is that triangle BCP is similar to triangle FEP. As we can see, angle B equals angle F, angle C equals angle E. Wow, so the what we just want to find, which is the ratio of CXF, area of CXF to the area of CYF. Well, this is just equal to the distances, the ratio of the distances, because we have the same base, CF, ratio of distances from X to CF and Y to CF, which is equal to the in radius of BCP, well, the in to the in radius of EFP. And because these two triangles are similar, in fact, similar with a ratio of 4 to 6, that tells us that the incenters have a ratio of 2 to 3. And that's your answer. Okay, good pace here, but we'll be done very soon. Number 8. How do we find, okay, so how do we deal with the sum? It's a very specific technique here. How do we deal with the sum, the infinite sum, n equals 0 to infinity of cosine of n theta over 3 to the n? What is this? Okay, the very specific technique here is, well, cosine n theta. So the denominator is 3 to the 0, 3 to the 1, 3 to the 2, and geometric sequence. What about the numerator? The numerator suggests, what is it called? De Moivre's cosine of n theta plus I sine of n theta. Excuse me, okay, equals cosine theta plus I sine theta to the nth power. We express this as e to the I theta. So we actually express, so cosine theta equals e to the I theta plus e to the negative I theta over 2. This is a very useful expression of cosine theta. Follows from this, and if you just take negative theta, that's cosine theta minus I sine theta. And in any case that we know, so cosine n theta is thus equal to same thing, but with e to the I n theta plus e to the negative I n theta over 2. And now this just becomes a geometric series, the sum of two geometric series. And the rest is computation, and you can rather easily do that. This, by the way, also facilitates us to find something like the sum of, say, cosine of n theta over n, if that converges, n squared if that converges. But in any case, that is doable similarly. I don't quite recall. There's a well-known fact about whether this converges or not. I'm not quite recall. I think it does converge, though. I may be wrong. But in any case, doing the same thing, writing cosine n theta as a geometric series, very useful technique. Number 9, we'll wait to, number 9 is a good problem. That's me being biased saying so, because it's, as a matter of fact, it's my own problem. I think it's one of the more straightforward problems here. It's less tricky, it's less technique specific. So in the interest of time, I'll just talk about number 10 and dismiss you guys. So number 10, well, spoiler alert, because the way we find this is, well, R, S, and T. So what do we know about R, S, and T? Well, we know R plus S plus T. It's not a particularly nice number. We know RS plus ST. So we know all the Vieta sums. But let's compare this with the roots of the original equation. So the sum of the roots is the same. The second sum, the sums of products of pairs of numbers, is also the same, but the product is 1/3 more. So what about our expression R cubed plus S cubed plus T cubed? The way we find this is consider expression R cubed plus S cubed plus T cubed minus 3 RST. And this is equal to R plus S plus T times, if you notice factoring, plus R squared plus S squared plus T squared minus RS minus ST minus RT. And well, we don't actually want to just plug in R plus S plus T and plug in whatever that might be. It's not the most pleasant thing possible, but we can compare this with the cube root of 13, the cube root of 53, and the cube root of 103. So product stays the same. This also stays the same. So we know that this expression for RST equals the same expression for cube root 13, cube root 53, cube root 103. All the terms are the same. And that expression would be not hard to find. Just plug it in here. And so that's equal to something that's 13 plus 53 plus 103 minus 3 times the cube root of their product. Which means that now if we but the important thing here is that this is equal to the same expression for cube root 13, cube root 53, cube root 103. So now if we want to find R cubed plus S cubed plus T cubed, well, that is equal to the same expression for root 13 cubed, excuse me, plus root 53 cubed plus root 103 cubed, except, well, our plus 3 RST. So R cubed plus S cubed plus T cubed equals this plus 3 RST. And the plus 3 RST is increased by 1. So just add 1, and that's your value. Anyway, pardon me for going over time, but thanks for coming. I hope that was enjoyable. Next week, you'll have, as an update, PSA, next week will be a team practice. Still, everyone is welcome to join. We do recommend that the teams that we have for HMMT, please try to, if you're in such a team, please try to show up next week and the week after. And I won't be there. Well, I won't be presenting next week. Instead, you'll have the illustrious Neil Yan to present for next week. So thanks for coming. See you next week.